Hello and welcome back. For those who are new at this channel, please do not forget to subscribe and hit the notification button for the new videos that are coming up. As you have seen, the videos are progressing from the bottom up through the OSI model layers. We have seen the physical and data link layer, and now we are focused at the network layer, where we will introduce you to the communication protocols and routing protocols. The objective of this module is to explain how routers use the network layer protocols and services to enable end-to-end connectivity. The topics that we will discuss will be the network layer characteristics, where we will explain how the network layer uses IP protocols for reliable communication. We will explain the role of the major header fields in the IPv4 packets. We will also explain the role of the major headers field even in the IPv6 packet. And we will explain how network devices use routing tables to direct packets to a destination network. And we also will explain the function of fields in the routing table of a router. The network layer provides services to allow end devices to exchange data across networks. As it is shown in the figure, the IPv4 and IPv6 are the principal network layer communication protocols. Other network layer protocols include routing protocols such as Open Short Path First and messaging protocols such as Internet Control Message Protocol. To accomplish end-to-end communication across network boundaries, network layer protocols perform four basic operations. The first one is addressing end devices, where end devices must be configured with a unique IP address for identification on the network. Encapsulation, where the network layers encapsulate the protocol data unit from the transport layer into a packet. The encapsulation process adds IP header information such as an IP address of the source and destination host. The encapsulation process is performed by the source of the IP packet. The other operation is routing. The network layer provides services to direct the packets to a destination host on other networks. To travel to other networks, the packet must be processed by a router. The role of the router is to select the best path and direct packets toward the destination host in a process known as routing. A packet may cross many routers before reaching the destination host. Each router a packet crosses to reach the destination host is called a hop. De-encapsulation is when the packet arrives at the network layer of the destination host. The host checks the IP header of the packet. If the destination IP address within the header matches its own IP address, the IP header is removed from the packet. After the packet is de-encapsulated by the network layer, the resulting layer 4 PDU is passed up to the appropriate service at the transport layer. The de-encapsulation process is performed by the destination host of the IP packet. Unlike the transport layer, which manages the data transferred between the processes running on each host, network layer communication protocols specify the packet structure and processing used to carry the data from one host to another host. Operating without regard to the data carried in each packet allows the network layer to carry packets from multiple types of communication between multiple hosts. In this animation, it is demonstrated the exchange of data at the network layer, where network layer protocols will forward transport layer PDU between hosts. As you can see at the source host, it is the encapsulation process, and at the destination host is the opposite, the encapsulation process, until the data reach the destination. IP encapsulates the transport layer segment or other data by adding an IP header. The IP header is used to deliver the packet to the destination hub. As it is illustrated here in the figure, the PDU of the transport layer is encapsulated by the network layer to create the network layer PDU, or as it is called, the IP packet. The process of encapsulating data layer by layer enables the services at the different layers to develop and scale without affecting the other layers. This means that transport layer segment can be readily packed by IPv4 or IPv6 or by any new protocol that might be developed in the future. The IP header is examined by layer 3 devices as it travels across a network to its destination. It is important to notice that the IP address information remains the same from the time the packet leaves the source host until it reaches at the destination hub, except when translated by the device performing network address translation for the IPv4. Routers implement routing protocols to route packets between networks. The routing performed by these intermediary devices examines the network layer addressing in the packet header. The data portion of the packet, that is the encapsulated transport layer PDU or other data, remains unchanged during the network layer process. We have to know that IP was designed as a protocol with low overhead. It provides only the functions that are necessary to deliver a packet from a source to a destination over an interconnected system of network. The protocol was not designed to track and manage the flow of packets. These functions, if required, are performed by the protocol at other layers, primarily as TCP at layer 4. The three basic characteristics of the IP are connectionless, which means that there is no connection with the destination established before sending data packet. It offers the best effort where IP is inherently unreliable because packet delivery is not guaranteed, and even media independent. It means that operation is independent of the medium, if it's copper, fiber optic, or wireless, who carry the data. IP is connectionless, which means that no dedicated end-to-end connection is created by IP before the data is sent. As we can see the analogy, the connectionless communication is conceptually similar to sending a letter to someone without notifying the recipient in advance. And this is summarized even in this figure. Connectionless data communication network work on the same principle. And as it is shown in this figure, IP requires no initial exchange of control information to establish an end-to-end connection before packets are forwarded. At the other side, IP also does not require additional fields in the header to maintain an established connection. This process greatly reduces the overhead of IP. However, with no pre-established end-to-end connection, senders are unaware whether destination devices are present and functional when sending packets, nor are they aware if the destination receives the packet or if the destination device is able to access and read the packet. The IP protocol does not guarantee that all the packets that are delivered will be received. The figure illustrates the unreliable or best effort delivery characteristics of the IP packet. As an unreliable network layer protocol, IP does not guarantee that all sent packets will be received. Other protocols will manage the process of tracking packets and ensuring their delivery. Unreliable means that IP does not have the capability to manage and recover from undelivered or corrupt packets. This is because while IP packets are sent with information about the location of delivery, they do not contain information that can be processed to inform the senders whether delivery was successful. Packets may arrive at the destination corrupted, out of sequence, or not at all. IP provides no capability for packet retransmission if any errors will occur. If out-of-order packets are delivered or packets are missing, the application using the data or upper layer services must resolve this issue. This will allow the IP to function very efficiently. In the TCP/IP protocol suite, reliability is the role of the TCP protocol at the transport layer. IP operates independently of the media that carry the data at lower layer of the protocol stack. As it is shown here, the IP packets can be communicated as electronic signals over copper cable, as optical signal over fiber, or wirelessly as radio signal. The OSI data link layer is responsible for taking an IP packet and preparing it for the transmission over the communication medium. This means that the delivery of IP packet is not limited to any particular medium. However, one major characteristic of the media that the network layer considers is the maximum size of the PDU that each medium can transport. This characteristic is referred to as the maximum transmission unit, MTU. Part of the control communication between the data link layer and the network layer is the establishment of a maximum size of the packet. The data link layer passes the MTU value up to the network layer. The network layer then determines how large packet can be. In some cases, an intermediate device, usually a router, must split up an IPv4 packet when forwarding it from one medium to another with a similar MTU. This process is called fragmenting the packet or fragmentation. Fragmentation causes latency. IPv6 packets cannot be fragmented by the router. We also have to know that IPv4 is one of the primary network layer communication protocols, and the packet header is used to ensure that this packet is delivered to its next stop on the way to its destination and device. An IPv4 packet header consists of fields containing information very important about the packet. These fields contain binary numbers which are examined by the Layer 3 process. The binary value of each field identifies various settings of the IP packet. Protocol header diagram, which are read as left to right, top to down, provides a visual to refer to when discussing protocol fields. This is a diagram where it identifies the fields of the IPv4 packet. The first one is version. It will contain a 4-bit binary value set to as 0100 that identifies this is an IPv4 packet. We have even the differentiated service field where it is 8-bit field used to determine the priority of each packet. The 6 most significant bits are the differentiated service code point, and the last 2 bits are the explicit conjunction notification bit. We also have the time to live field where it's the 8-bit binary value that is used to limit the lifetime of a packet. The source device of the IPv4 packet sets the initial time to live value. It is decreased by 1 each time the packet is processed by a router. If the time to live field decrements to 0, the router discards the packet and sends an Internet Control Message Protocol time exceeded message to the source IP address. Because the router decrements the time to live of each packet, the router must also recalculate the header checksum. The other field is the protocol field, where it is used to identify the next level protocol. It is 8-bit binary value that indicates the data payload type that the packet is carrying, which enables the network layer to pass the data to the appropriate upper layer protocol. Common values are 1 for the Internet Control Message Protocol, 6 for TCP, and 7 for UDP protocol. We even have the header checksum. This is used to detect corruption in the IPv4 header. The last 2 fields are 32-bit binary value for the source IPv4 address and the destination IPv4 address, where the first one represents the source IPv4 address of the packet, and this is always a unicast address, and the second one represents the destination IPv4 address of the packet. The destination IPv4 address is unicast, multicast, or even a broadcast address. The two most commonly referenced fields are the source and destination IP addresses. These fields identify where the packet is originating from and where it is going. These addresses do not change while traveling from the source to the destination. The Internet header length, the total length, and header checksum are used to identify and validate the packet. Other fields are used to reorder a fragment packet. Specifically, the IPv4 packet use identification, flags, and fragment offset to keep tracking of the fragment. A router may have to fragment an IPv4 packet when forwarding it from one medium to another with a smaller MTU. There are even other fields as option and padding field, but there is not our topic. Even the IPv4 is still in use today, we need to learn about the IPv6, which will eventually replace IPv4. To better understand why we need to know the IPv6 protocol, it will have to know the limitation of IPv4 and the advantage of the IPv6. Through the years, additional protocols and processes have been developed to address new challenges. However, even with the changes, the IPv4 still has three major issues. The first one is that the IPv4 addresses depletion, which means that IPv4 has a limited number of unique public addresses available. Although there are approximately 4 billion IPv4 addresses, this increasing number of new IP-enabled devices, always on connection, and the potential growth of the less developed regions have increased the need for more addresses. The other issue is even the lack of end-to-end connectivity, where the network address translation is a technology commonly implemented within IPv4 networks. This provides a way for multiple devices to share a single public IPv4 address. However, because the public IPv4 address is shared, the IPv4 address of an internal network host will be hidden. This can be problematic for technologies that require end-to-end connectivity. The last issue is the increased network complexity. While network address translation has extended the lifespan of IPv4, it was only meant as a transition mechanism to IPv6. Network address translation in its various implementations create additional complexity in the network, creating latency and making troubleshooting even more difficult. Depending on the issue, in early 1990s, the Internet Engineering Task Force began to look for the replacement of IPv4. This activity led to the development of IPv6, who overcomes the limitation of IPv4 and is a powerful enhancement that with feature that better suit current and foreseeable network demand. Improvement the IPv6 provide increased address space where IPv6 addresses are based on 128-bit hierarchical addressing as opposed to IPv4 with 32 bits. Improves even the packet handling where the IPv6 header has been simplified with fewer fields and will also eliminate the need of NAT. With such a large number of public IPv6 addresses, NAT between a private IPv4 address and a public IPv4 is not needed anymore, and this will avoid even some of the NAT-induced problems experienced by applications that require end-to-end connectivity. And in this table, it is shown the address space comparison between the IPv4 and the IPv6. Till here is the number of the address available for IPv6, around 4 billion IPv4 addresses, and here is the limitation for the IPv6, where it's around to 340 on the ceiling IPv6 addresses. The major design improvement IPv6 over IPv4 is the simplified IPv6 header. The IPv4 header consists of variable length of header of 20 octets and 12 basic header fields, without including the option field and padding field. In this figure are highlighted some fields that have remained the same, some fields where they have changed names and position, and some fields that are no longer required for IPv6. And as in contrast, the simplified IPv6 header shown in this figure consists of length of header for 40 octets and will allow more efficient processing of IPv6 header. The fields of IPv6 header are the version, where it is 4-bit binary value that's set as 0110, who identifies the IP as an IP version packet. We have even the traffic class, which is 8-bit field and is equivalent to the IPv4 differential service field. We have even the flow label, which is 20-bit field that suggests that all packets with the same flow label receive the same type of handling by routers. We have even the payload field. This is 16 bits and indicates the length of the data portion or payload of the IPv6 packet. This does not include the length of the IPv6 header, which is fixed as 40-byte header. We have even the next header field, which is 8-bit and is equivalent to the IPv4 protocol field. It indicates that data payload type that the packet is carrying, enabling the network layer to pass the data to the appropriate upper layer protocol. We have even the hop limit that is 8-bit also and replace the IPv4 time to leave field. This value is decremented by 1 by each router that forward to the destination of the packet. When the counter is 0, the packet is discarded and an Internet Control Message Protocol version 6 time exceeded message is forwarded to the sending host. This indicates that the packet did not reach its destination because the hop limit was exceeded. Unlike IPv4, IPv6 does not include an IPv6 header checksum because this function is performed at both lower and upper layer. This means that the checksum does not need to be recalculated by each router when it decrements the hop limit field, which also improves the network performance. The last two fields are the IPv6 source address and IPv6 destination address. These are 128-bit fields, and the first one identifies the sending host and the second one identifies the receiving host. An IPv6 header may also contain extension headers, which provide optional network layer information. Extension headers are optional and are placed between an IPv6 header and the payload. Extension headers are used for fragmentation security to support mobility and many more. So with this, we are ending the first three topics of the network layer. So we saw network layer characteristics and we compared the IPv4 and IPv6 headers. Thank you for being with me. Do not forget to subscribe at this channel and hit the notification button for the new videos that are coming up.